guys, Spider Derivative Man here, talking to you about comparing graphs of a function and its derivative. Now here's a question. What day do spiders not skip at the gym? Leg day!
First vocabulary term is a tangent line. That's a line that touches a curve at one point without crossing through it. So here you can see we have a black function, and then this red line right here is a tangent line because it touches the black function at one point, point P, the point of tangency, and then continues on. It doesn't go through the black function. It doesn't cross through it at 2 points. It just touches it at one point and then continues on. Over here we have our red function, and the blue line is tangent to the curve at this point, the point of tangency, but it also crosses through at another point. So technically this line we cannot consider a tangent line. We're going to call it something else. But we can say that this blue line is tangent to the curve at this one point because it goes up, touches the red curve at one point, and then continues on. Now, because it touches the curve at 2 points, you can call it a secant line. A secant line is a line that intersects a curve at 2 points. So here we have our blue function, and this purple line is our tangent line because it goes up, it touches the blue function at 1 point, and then continues on. Remember, this is the point of tangency. The red line, you can see, intersects the blue function at 2 points. Because of that, we call that a secant line. Same thing over here. We said this blue line is tangent to the curve at this point, the point of tangency, but because it intersects the curve at 2 points, we technically call this blue line a secant line instead of a tangent line. Now, the derivative of a function at x is the instantaneous rate of change, or amount by which a function changes at a given x value. The derivative of a function is equal to the slope of the tangent line at a given x value. Now, the first thing I want you to do is note that there's 3 things here that mean the exact same thing. The derivative of a function at x is the same thing as the instantaneous rate of change at a particular x value, which is the same thing as the slope of the tangent line. So all 3 of these things mean the exact same thing. So now let's look at our 2 examples down here. In this first example, we have a blue curve. This is our function. And let's say I want to find the instantaneous rate of change, the derivative of the function at x equal to 1. So I want to find the slope of my function at one particular x value, x is equal to 1. All I have to do is draw my tangent line to the curve at that particular point. So here we have this red tangent line that goes up, it touches the curve at one particular point, and then continues on. This tangent line, if I were to find the slope of it, it will give me the derivative of my blue function at x equal to 1. It will give me my instantaneous rate of change at one particular x value, x is equal to 1. It'll give me the slope of my function at one particular x value, x is equal to 1. That is what this is talking about. So anytime you hear derivative of a function at a particular x value, it's talking about the slope of the function at that particular x value. It's talking about the instantaneous rate of change at a particular x value. It's talking about the slope of the tangent line. All of those things mean the same thing. Now let's look at this example over here. Here we have our function in red, and our tangent line is this blue line. And it's showing you the tangent line to the curve at different x values. So as we increase in x values, you see how the tangent line to the graph changes as our x values increase here.
Example time!
Now example 1 says estimate the slope of the graph at the points x sub 1 comma y sub 1 and x sub 2 comma y sub 2. So here we have our blue function, and we have 2 points, x sub 1 comma y sub 1 and x sub 2 comma y sub 2. And we want to estimate the slope of the graph at these points. So here we're just estimating. So how do we estimate the slope of the graph at a particular point? We get the tangent line to the graph at that point. So we draw a tangent line to the graph at this particular point. So if we're starting with x sub 1 comma y sub 1, we're going to draw a tangent line to the graph here. Now notice x sub 1 comma y sub 1 is at a relative maximum, meaning that if we were to draw a tangent line, it would actually be a horizontal line. Now, if we want to estimate the slope of the function at this particular point, the instantaneous rate of change at this particular point, the derivative of the function at this particular point, it's just the slope of the tangent line. And a horizontal line has a 0 slope. So we're going to say that the slope of the function at this particular point, x sub 1 comma y sub 1, is 0. Let's do the same thing for x sub 2 comma y sub 2. So again, in order to estimate the slope, I need the tangent line to the graph at that particular point. Once I have drawn the tangent line to the graph at that particular point of tangency, I can then get the slope of this line by just choosing 2 points that are on this line. I can then take those points, plug them into the slope formula, and solve for our slope. So I'm going to say this is a point, right, at 4, 2, and then another point here at 3, -1. So if I were to plug those 2 points into the slope formula, or I could just count rise over run, looks like I'm going up 3, right 1, so that's going to be 3 over 1. So this is going to be a slope of 3 for this particular line. So remember, this means that the slope of the function at this particular point, the instantaneous rate of change of the function at this particular point, the derivative of the function at this particular point is equal to the slope of the tangent line at this particular point, which is 3. Part B, we have 2 points, x sub 1 comma y sub 1 and x sub 2 comma y sub 2. Again, if we want to estimate the slope of the function at this particular point, we need to draw the tangent line to the function at that particular point. We can then calculate the slope of this line, and that's going to be equal to the slope of the function at this particular point. So again, to calculate slope of a line, we need 2 points. So how about 4, 12, this point, and then this one, 6, 4. So if we plug those into the slope formula, we end up getting -4 as our slope, which means that the slope of the tangent line to the function at this particular point, the slope of the function at this particular point, the derivative of the function at this particular point, the instantaneous rate of change of the function at this particular point is -4. Now we got to do the same thing with x sub 2 comma y sub 2. We again draw a tangent line to the graph at this particular point. Because x sub 2 comma y sub 2 is a relative maximum, we again get a horizontal line. To calculate the slope of a horizontal line, you don't have to do anything. It's just 0. So we know that the slope of the tangent line to the function at this particular point, the slope of the function at this particular point, the derivative of the function at this particular point, the instantaneous rate of change of the function at this particular point is 0.
My spidey sense is tingling. Must be time for a U-try.
Okay, doing the same thing. So we have x sub 1 comma y sub 1. Again, to calculate the slope of the function at this particular point, we need to draw the tangent line. We have a relative minimum in x sub 1 comma y sub 1, which means that the tangent line that we draw is going to be a horizontal line. Because of that, it's going to have a slope of 0, which means that the slope of the tangent line to the graph at this particular point, the slope of the function at this particular point, the instantaneous rate of change at this particular point, the derivative of the function at this particular point is 0. Here we have a point, and we want to estimate the slope at this point, so we draw a tangent line. We then calculate the slope of this line, which will then give us the slope of the function at this particular point. So how do we calculate the slope of this line? Well, we choose 2 points. We have -1, 9. That's 1 point. And then it looks like we have another point at 1, 6. So that would be down 1, 2, 3, right 1, 2. So that would be -3 over 2. And that would be the slope of the line tangent to the curve at this particular point. Slope of the function at this particular point, the derivative of the function at this particular point, the instantaneous rate of change at this particular point. We have 2 points over here. Let's start with our x sub 1 comma y sub 1. We draw a line that is tangent to the graph at this particular point. We then calculate the slope of the function using 2 points that are on this given line. So it looks like we have a point here and a point here. To calculate the slope, looks like we're going down 1, 2, 3, 4, 5, and over to the right 1, 2. So -5 over 2 would be the slope of this line tangent to the curve at this particular point. It would be the instantaneous rate of change of the function at this particular point. It would be the slope of the function at this particular point. It would be the derivative of the function at this particular point. Let's do the same thing for x sub 2 comma y sub 2. We draw a line tangent to the curve at that particular point. We then choose 2 points that are on that line. So we have a point here, and it looks like we have our point of tangency that we can use. So we go up 1, 2, 3, 4. So it's going to be 4 over 1, 2, 3. So 4/3 then is going to be the slope of the tangent line to the graph at this particular point. It's going to be the instantaneous rate of change of the function at this particular point. It's the slope of the function at this point. It's the derivative of the function at this point. All of those things, remember, mean the same thing. Now we have the whole point of the lesson here, comparing graphs of the function and its derivative. So what you need to know is that the slopes of the original function, or the tangent lines to the original function, correspond to the y values of the graph of the derivative. So if you're looking at a quadratic function right here, you can see that the slope of the function, or the slopes of the tangent lines to the function as x increases, they are negative, but they are getting less and less and less negative until you have a slope of 0 right at this particular value. then the slopes start increasing. Now you can see down here that the y values start very negative, and they get less and less and less negative until at this x value, you have a horizontal tangent line, meaning that the slope of the function, the slope of the tangent line, is equal to 0. That's why the y value of this graph of the derivative is equal to 0. Then the slopes of your function start increasing, the slopes of the tangent lines to the function start increasing, therefore the y values of the graph of the derivative start increasing. Again, you just need to know that the slope of your function, or the slopes of the tangent lines to your function at any given x value, correspond to the y values in the graph of the derivative. Now, example 2 says match the following graphs to the graphs of their derivative. So up here, we have the original functions, and then down here, we have the graphs of their derivatives. Now, these problems come up all the time. We're going to have a bunch of these on the tests and quizzes. These appear on the AP test all the time. In order to do this, you need to understand the relationship between the original function and the graph of the derivative. So if we think about the derivative of a function, it's going to be the slope of the function at a particular point. It's going to be the slope of the tangent line to the curve at a particular point. Down here, how that's going to appear is the slope of the function at a particular point, the slope of the tangent line to the function at a particular point, the derivative of the function at a particular point, is going to correspond with the y values in the graphs of your derivative. So let's do an example. Part A, we have this function. Now notice, if I were to calculate the slope of the function at any value here, it would be negative. Think about drawing a tangent line to the curve. At any point, the slope would be negative. You would draw a line with a negative slope. Now, initially, if I were to draw a tangent line here, it would have a really negative slope, but then the slopes would get less and less negative as I kept drawing my tangent lines, meaning that we should start off with a really negative y value down here, and then they should get less and less and less negative, but they will still stay negative the entire time because any tangent line that I draw has a negative slope. So which y values down here start off very negative and stay negative the whole time? That looks like this one, right? We start off very negative, and then they get less and less and less negative as x increases. So we can say that the function for part A matches with the derivative number 3 down here. Part B, we have this function. Now again, let's imagine drawing a tangent line to the curve at a bunch of different points. So here initially, we have a tangent line that has a slightly positive slope. And then as x increases, the tangent lines get a more and more positive slope until at x is equal to 0, I have a slope of about 1, let's say. And then after x is equal to 0, the tangent lines that I draw, their slopes are less and less and less positive, meaning that down here, the y values should start off somewhat positive and then approach 1 and then get less and less and less positive. But they're still positive the whole time. The slopes of the tangent lines for this particular function are never negative. So which graph down here has y values that are always positive and approach 1 at x is equal to 0 but then get less positive? That would be this one right here, right? We have y values that are positive and then get more and more and more positive. And as x approaches 0, we get a y value of about 1, which means the slope of this graph has to be 1, and it looks like it is. And then it gets less and less and less positive because the slopes of your tangent lines that you draw get less and less positive. So B will go with 4 down here. Let's look at C. If I were to draw tangent lines to the curve here, they would have slopes that are very, very, very positive. And then as your x increases, the slopes of your tangent lines would get less and less and less positive until at x equal to 2, we would get a tangent line that has a 0 slope. Then after that, the slopes of the tangent lines that you draw to this function would get more and more and more negative, which means that if we were looking at the derivatives down here, the y values for the graphs of our derivatives should be very positive, so big positive numbers that slowly decrease until you get to a y value of 0 at x is equal to 2. And then the y values down here should start decreasing until you get really, really, really negative numbers past x is equal to 4. So which one of these graphs that we have left start off with really positive y values, then go to 0 at x is equal to 2, and then get more and more and more negative? That would be number 2 right here. Now let's look at D. So for D, we look at the tangent lines that we draw. If we were to draw tangent lines to this graph, the slopes would be negative, 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 and then at about x is equal to negative 1.75, we have a 0 slope of our tangent line. Then after that, the slopes of the tangent lines you draw to the graph are positive. Then at about x is equal to 1.75, we have again a horizontal tangent line, meaning the slope of our tangent line is 0. So then after that, the slopes of the tangent lines that we draw to the graph are negative again. So we are looking for, down here, y values that start off negative, then become 0 at about negative 1.75, then become positive again, then become 0 at 1.75, and then become negative again. So if we were to look at these two graphs, it looks like this one has negative y values until negative 1.75, then it becomes 0. Then we have positive y values until 1.75, that's where we have another 0, and then negative again. So again, the y values down here correspond with the slope of this function at any given x value. Lastly, we know that e will have to go with I, and the reason for that is because we have the slopes of this graph, or slopes of the tangent lines drawn to this graph, that are negative, 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 and then at x is equal to 0, we have a horizontal tangent line, meaning the slope is 0. So you can see at x is equal to 0, we have a y value of 0 for our derivative, because again, the y values correspond with the slope of our function. After x is equal to 0, the slopes of this graph, or slopes of the tangent lines drawn to this graph, would be positive. So you can see we have our graph above the x-axis, meaning positive y values.
You try.
Okay, doing the same thing. So let's start with A. Notice this graph is not curved. We have a line segment and a line segment. So in this particular graph, the slope of this portion of the graph is a positive slope, but it's constant. It's the same slope all the way throughout until you get to this given x value, this negative x value, whatever it is. After that, the slope is then 0 because it's a horizontal line. So we're looking down here for a graph that has a y value that is positive because we have a positive slope here, and then at around x is equal to negative 1, it becomes 0 for the rest of the graph. So a y value that's positive, and then at around x is equal to negative 1, we get a y value of 0 for the rest of the graph. That would be D right here. For part B, again, notice that we do not have a curve. These are line segments, meaning that this is a constant negative slope, followed by a constant positive slope, followed by a constant negative slope, followed by a constant positive, constant negative, constant positive. Now, what does that mean for your graph down here? That means that the y values of a given graph should just be a negative number, then a positive number, then a negative number, then a positive number, then a negative number, then a positive number. So this graph right here, the graph of f, you can see has a constant negative y value, then a constant positive y value, then a constant negative y value, then a constant positive y value, because the slopes of this graph correspond with the y values of this graph. For C, we look at the graph and we see that it has, if we were to draw tangent lines to the graph, the tangent lines start off pretty close to 0, then increase and become positive. Then around x is equal to 0, we get a horizontal tangent line, meaning the slope of our tangent line is 0. Then after that, the slope of our tangent lines get negative and then round off to 0 towards the end. So we should be looking for y values down here that start off around 0, become positive, then become 0 again at x is equal to 0, and then become negative afterwards. So y values that start off positive, and then around x is equal to 0 become 0, and then become negative afterwards. So that would be B right here. For part D, we're doing the same thing. We have our function here. Now let's pretend we're drawing a tangent line to this function. Initially, the slopes of those tangent lines would be negative, and they would get increasingly more negative as x approaches 0, until as you get closer and closer and closer to 0, the tangent lines almost have a slope of negative infinity. Then after x is equal to 0, the slopes are super positive. They're almost positive infinity. And then as x increases, the slopes of your tangent lines get less and less and less positive, but are still positive. So we are then looking for y values down here that start off negative and then get increasingly more negative as x approaches 0. And then after x is equal to 0, they start off super positive and then get less and less and less positive. So that would be C right here. Let's check out E up here. We again draw tangent lines to this curve right here, and you can see that the slopes of those tangent lines start off at 0 and then get increasingly positive until at about x is equal to 0, we have a slope of about 1. And then after x is equal to 0, the slopes are still positive for your tangent lines, but get closer and closer and closer to 0. So we are looking for positive y values down here that get close to 1 around x is equal to 0, and then start decreasing after that, but are still positive. That would be A right here. Positive y values that get close to 1 1 around x is equal to 0 and then get less positive. Lastly, f we know goes with e, and the reason for that is you can see that we initially start off with tangent lines that have slopes of nearly infinity and then get less and less and less positive as x approaches 0 until we reach x is equal to 0 and have a slope of our tangent line of 0. So you can see that the y values here correspond with that. We have very positive y values and then they approach 0 as x equals 0. And then after that, the slopes of those tangent lines would be negative and they would get increasingly more negative as x increases. So you can see the y values get increasingly more negative as x increases. Now, example 1 says sketch the graph of the derivative of the function. So here we have our function f, and we know that it is a parabola, meaning that it must be a quadratic function. Over here, we are going to sketch the graph of the derivative of this function. Now, it's important to remember that in the graph of the derivative, the y values are going to correspond to the slope of your function over here, or the slopes of the tangent lines to this function. So if we were to start at x is equal to -3, we see that our slope of our function is negative, and it's pretty negative. Now that means that the y values of the graph of our derivative around x is equal to -3 should be pretty negative. As we increase in x values though, you see that the slope of your function, the slope of the tangent lines to the function, are still negative, but getting less and less and less negative until at x is equal to -1, we have a horizontal tangent line, meaning that the slope of our function at x is equal to -1 is 0. So our graph of our derivative should then have a y value equal to 0, and it does. After x is equal to -1, the slope of our function, or the slopes of the tangent line to the function, are positive and start increasing. They start getting more and more and more positive, meaning that the y values over here should be getting more and more positive after x is equal to -1, and they do. Therefore, we have now graphed our function and its derivative.
Don't be a vulture. Do your own work. You try.
Okay, doing the same thing here. Remember, in the graph of our derivative, the y values are going to correspond to the slope of our function, or the slopes of the tangent lines to the function at any given x value. So in this graph of f, at the beginning over here, we see that our slope of our function, or the slopes of the tangent line to the function, are very positive, meaning that we should start off with y values that are very positive. Then, as we increase in x values, you see that the slopes of the tangent lines to the function, or the slope of the function itself, is positive, but getting less and less and less so, until at x is equal to 0, we have a horizontal tangent line, meaning that the slope of our function is equal to 0, meaning that the y value of the graph of our derivative should also be 0, and it is. Then after that, the slope of our function, or the slopes of the tangent line to the function, start getting positive again. They start off with very, very small positive slopes and then continue to get greater and greater, meaning that the y values in the graph of our derivative should start off very small and positive, but continue to get greater and greater and greater, and they do. Therefore, we have now graphed the function and its derivative here. Kind of interesting that the derivative of the cubic graph was a quadratic graph, and the derivative of a quadratic graph was a linear graph. Might be something to that later on.